So in the last part of this unit, a unit on current, we examined Ohm's law and the relationship between current, voltage, and resistance. Okay, and that's all well and good, but as normally when we study something, we want a practical purpose behind it, and that's where electrical power comes in. So electricity in general, okay, we use electricity as people to not use the electricity directly necessarily, but take it and transfer it into some other type of energy that becomes useful to our daily lives. For example, our lights. We use electricity to change electricity into light energy in a light bulb, or we may use it to create heat in a furnace in a house, or we can turn it into mechanical energy to run a drill or run other such objects, a CD player to turn the CD around, or any of these things. I mean, not that people still use CDs with downloading music, but you get the idea. Um, so electrical power then, okay, again, we transform electrical energy into some other form of energy. So if you remember, power is the rate of transformation of energy. So this goes back to last year's classes, and we have power is equal to a change in energy over time. So it gives us how quickly we can take that electricity and turn it into heat, and how efficiently that can be done. Okay, now we also know from our previous units on electric fields, if you remember, energy, a change in energy, is just equal to the amount of work that's done in a system. And work, in terms of electric fields, is the charge that's being transferred times the potential difference, or the voltage. Okay, so if we combine these two equations together, we get P is equal to QV, charge times voltage, divided by time. And you may notice something from the last unit here. We have this charge over time term here, which, if you remember, charge over time is equal to current, which gives us the equation P equals IV, or power is equal to current times voltage. So this will give us the power if we take the current of an object, or the current. So if we look at a general house, say, and a house supplies a 240 volt current in our wall, or sorry, a 240 volt voltage, and we multiply that by the current coming out, we can get the power. So this is the power being generated by a system, or the power required by a system. If we want to know the power that's lost or dissipated in a resistor, we may not actually know the voltage across that resistor. So we have to change our equation just a little bit. So using Ohm's law, if you remember, is V in simplest terms, V equals IR, voltage equals current times resistance. Then we get power, substituting this in, is equal to I times IV, or power is equal to I squared R. Okay, so this equation, again, the equation at the top is giving us the total power in a system, whereas the equation here, P equals I square R, this is giving the power that's lost or dissipated in a resistor. Okay, both of these are going to become important for solving problems. Speaking of, example 1. So suppose that you're operating a 1,800 watt hair dryer at a household voltage of 240. So you plug it in, you look at your hair dryer, it tells you the wattage on the hair dryer, and this is the voltage that your house supplies. Okay, assume the power must be sent over a distance of 300 kilometers over wires that have a resistance of 1.0 times 10 to the negative 5 ohms per meter. So we're pretending here, so this voltage doesn't just come from your plug when you plug it in. This voltage is coming from a power plant that is 300 kilometers away. So it has to travel all this way over wires which have resistance themselves, like we looked at when we studied resistivity. Okay, so it has to come through these wires. So we're going to lose, because of this, we're going to lose some of that power, by the time it actually gets to our house. So what we want to determine is what percentage of the power is lost transferring that energy from a power plant all the way to power the hairdryer in your house if the power is sent at 240 volts. Okay, so if at the power plant it's 240 volts leaving there, what is it when it gets to our house? And then we're going to look at how much power is lost if it's sent at 12,000 volts. Okay, so for part A, we have our power that the hairdryer requires is 1800 watts. Okay, our voltage from the source is 240 volts, and we can find our resistance. So we saw that the wire, it said, had a resistance of 1.0 times 10 to the negative 5 ohms per meter, ohms per meter, and that it's being sent over 300 kilometers, or 3 times 10 to the 5 meters. So by multiplying this, we can get the total resistance that our current has to travel through, which is 3 ohms. Now, if you think wires are quite thick, so 3 ohms, reasonable resistance. This is our so then we can start our calculation. So we can figure out for first thing is the current that our electricity is traveling using P equals IV because we have our total voltage and our power. P is 1800 watts times I, and voltage is 240 volts. So we get that the current will be traveling at 7.5 amps. Now remember, resistance is a constant here. The resistance of these wires doesn't change. So what we're altering is a play between the voltage and the current. So a low voltage will mean a high current. A high voltage means a low current. So then we can find our power that's lost in this system using I squared times R. So we have our I is 7, so we have 7.5 squared times our resistance of 3 ohms. That gives us a power loss of 170 watts. Finally, we can plug this in and calculate. So we have our power lost as 170 over the total power, or our total operating power is 1,800. Okay, we divide those times 100, and that gives us 9.4%. So 9.4% is the amount of power lost if we send the power at 240 volts. Okay, so let's see what happens if we send the power at 12,000 volts. So the difference here, so our power is staying the same, send the voltage at 12,000 volts. So power of our hairdryer does not change. The voltage now is 12,000 volts. The resistance is still going to be the same as well because we're not changing the wires that it travels through, so 3 ohms. So we start the same process. We have power is equal to current times V to find our current that it's traveling, which will then let us find our lost power. So 1800 equals I times 12,000. I, or our current, is 0.15 amps. Okay, we then get our power that's lost in the system by doing I squared times R. 0.15 squared times 3, which is 0.068, much smaller than the last one. So then we take our watts, or our power that's lost, 0.068, over our total power that's used to power the hairdryer, times 100, and we get 0.0038%. Okay, so with a high voltage, with a low current, we actually significantly drop the amount of power that's lost over transport. So this is why the wires outside on the telephone poles, this is why they use such a high voltage. So it actually, they transport it at an incredibly high voltage from the power station. And then if you look at some of those telephone poles outside your house, some of them will have boxes on them. And what those boxes are transformers. Because we don't want the voltage coming into our house at 12,000 volts. We want a voltage at 120 or 110 or 240, depending on where you live. So those transformers take that really high voltage and convert the high voltage and low current, and they swap it to a high current and low voltage flow. We're going to examine transformers later on in this unit when we study more on circuitry. That's just a quick little intro to them right now. So with all this power, so yeah, we can run a hair dryer. We can figure out how much power and how much voltage we need to run the hair dryer. But an important question is how much does all of this cost? Okay, so companies measure the energy usage in what we call kilowatt hours, or kW, kilowatts times an hour. Okay, a kilowatt hour, it's not quite a joule. It's a little bit of a different measurement, but it's the same idea of units. It's a measurement of energy. So you can imagine it in joules. There would be a conversion number that you can calculate to figure out how you would go from from kilowatt hours to a joule, which would be a watt second. Okay, that's the difference. So a watt second versus a kilowatt hour. Kind of like changing from meters per second to kilometers per hour, except with energy. Okay, so energy and power, we know, are related by the following equation. We have power is equal to a change in energy over time, or we can rearrange that to give us a change in energy is equal to power times time. So power being in this case, we want it in kilowatts and time being in hours. Okay, the cost of electricity, at the time I originally looked this up, we're going to use this value as we calculate it, so 0.118 kilowatt hours. So $0.118 per kilowatt hour, I should say, is the cost of electricity here in Nova Scotia. Now, this was an older cost. I accidentally looked up an older document. The cost of electricity currently it changes between peak hours, so during the day versus in the night. But the cost during peak hours at this time of year is actually around not 11 cents, but around 20 cents per kilowatt hour. So it's actually almost double the cost at certain times. Now, in off-peak hours, it drops down to around 8 cents per kilowatt hour. So on average, we're looking at electricity usage in Nova Scotia of around 14 cents or 0.14 per kilowatt hour. But we'll use this value for all of our calculations we do. Okay, so an example, how much would it cost to operate two 75-watt light bulbs for 3 hours a night for 30 days? Okay, assume the cost of electricity is $0.118 per kilowatt hour. So first we want to take our power. So our total power is going to be 150 watts since we're using two 75-watt light bulbs. We just want to convert that to kilowatts by dividing by 1,000 because we're looking for kilowatt hours. Our time, so 3 hours a night times 30 days is going to give us a total of 90 hours of usage. And our goal here is to figure out how much does that cost. Okay, so we can start. So remember, kilowatt hours is energy. Just another type, instead of measuring though in joules, watts times a second, we measure in kilowatt hours. So we use our equation for energy, which is power times time. We get 0.15 kilowatts times our 90 hours that it runs for is 13.5 kilowatt hours. Okay, we can then calculate the cost. It's the cost of electricity. We have 13.5 kilowatt hours times the cost is $0.118 per kilowatt hour. Okay, so the kilowatt hours here, units will cancel out, leaving us with units of dollars, and we're left with 1.59 or $1.59 to run these 275-watt light bulbs for 3 hours a night for 30 days. Okay, so another practice problem. An air conditioner draws 12 amps on a 240 volt line. How much does it cost per month? So if you're running for 30 days, if it operates at 7 hours per day, assume the cost of electricity again is $0.118 per kilowatt hour. So take a minute, pause this, take a minute to solve this problem before coming back to look at the answer. Okay, so we'll write down our information that's given. So we have our current is 12 amps. Our voltage is 240 volts. Our time is going to be 7 times 30, or 210 hours, 7 hours a day for 30 days. And our rate, as we'll use for any calculations we do, 118 dollars per kilowatt hour. Okay, and our goal here again is to find the cost. So we can start this. We're going to need to find energy, but to find energy we need power. So our total power of the system, again, we're not calculating power lost, we're looking at how much is used. It's going to be current times voltage. 12 times 240 gives us a power of 2,880 watts, or 2.88 kilowatts. Okay, we then calculate our energy. Energy is equal to power times time, which we get 2.88 kilowatts times 210 hours gives us energy in terms of kilowatt hours as 605 kilowatt hours. And lastly, our cost, which will be our kilowatt hours, so 605 times our cost of electricity, $118 per kilowatt hour, gives us a total of $71.39. Okay, quite a bit to run an air conditioner for a full month. And if you remember now, I was saying this cost is actually about almost double what it is here. So you can imagine the same situation now in Nova Scotia. It's actually costing over $100 per month to run an air conditioner for 7 hours a day. Okay, so that brings us to the end of the power section. The next section we're going to look at it in the next videos. We'll actually start studying circuits and looking at parallel and series circuits. But for right now, this is the end of power. So your homework is to go on and try section 3.3.2 or 3.2.2, the couple of problems that are in there. Good luck.